Okay, it's 4 o'clock, so I think we will start it.
Yeah.
Sir.
Yes.
So good afternoon, all. Welcome to this first webinar on currents and course. Together here we have Professor Sriram, and along with Professor Sriram is my co-organizer, who is Vinay from IIT Jammu. So it's our pleasure to have Professor Sriram from IIT Madras, working in Department of Ocean Engineering. And to kick off this series, he's going to talk about hybrid numerical modeling in ocean engineering. So the format of this webinar series is going to be a research presentation in the beginning for about 20 to 25 minutes, and followed by the research presentation. Me and Vinay are going to ask a couple of questions as hosts, and followed by this, the floor will be open for audience for further questions technically. So with this introductions, I would request Professor Sriram to start. Please start the presentation.
Yeah. Thank you.
Anand, we could not able to see the screen.
Oh, is it
Okay.
shared? The screen is shared or not?
Yeah, I can see it, but
you minimize the Teams window.
Is it?
Yeah.
Okay. Yeah, I will do it. Sorry. Yeah.
Achha, so it's yours.
Yeah.
Okay.
Yeah,
Okay.
Sure. Fine. You can able to see now?
Yes, sir. We can see you. Yeah.
Okay, fine. Sure. Okay. Thank you, Anand, as well as Vinay. This is very nice initiative from the young researchers, because I know that I have seen these kind of initiatives in abroad, but this is the first time I have seen these kind of initiatives in India. So first of all, congratulations for initiating this, as well as I think it will go a long way with inviting a lot of other people in the field. So just to begin the talk, I will try to give about 25 minutes to 30 minutes, roughly of that order, about some of the developments in the numerical model, particularly in handling the wave structure interaction process in India, as well as in abroad, wherein people have tried to develop different types of numerical models in the past, as well as what is happened in the present, what is the current scenarios in the present situation, and what could be the future, what is the thing which we are going to expect from the future. So this talk is mostly addressed towards about my journey from the beginning. For the last 15 years, I'm basically working in this particular area of the development of the numerical model. During my postdoc, as well as after I came back to IIT Madras along with my students, I try to develop some of these models that are applicable to the industry. So just to give you the overview of the talk. So first, I will try to discuss about some of the challenges as well as the modeling approach that are exist in the today's context, along with the different class of numerical models, particularly to address the wave structure interaction process. And then apart from that, I will, after doing the classification of the numerical models, I will try to bring in the hybrid modeling. How do we do a hybrid modeling? Why we need the hybrid modeling? What is the requirement for it? Both the two-dimensional as well as the three-dimensional coupling. I will try to cover some of the applications related to nowadays the boom is on renewable energy, for example, floating renewable energies, or for in the coastal engineering, if you try to look at how do we model the vegetations, whether it's a micro scale or macro scale modeling, as well as the naval architecture aspects with the ship motions and ship wakes, how we can able to understand this aspect, as well as along with the tsunami flows and the wave impact. So this is what I will try to bring in some of those things. I may not able to go into the details of each of these aspects because of the time constraint, but I will try to give an overview of the short, how we basically develop, what is happened in the past, what is current, and what could be the future in this aspect. So if you look at the motivation or introduction to the ocean engineering part, there are two things which we normally do. There is two challenges which we normally have. One is basically the if you look at the ocean engineering perspective, we are also going to have a large spatial domain as well as the time scale. Say, for example, if you have a breakwater or a groin field, the sediment transport phenomena is going to, it's a large spatial domain, correct? As well as the time scale is going to be of the order of years to develop. So it is not going to be a short-term contribution. Or in the same aspect, we do also have a small spatial as well as the time scale, wherein if you are trying to look at the structural impact due to breaking waves, which is of order of seconds, basically. So that means one need to develop the numerical model that can able to understand this large spatial domain as well as the time scale, because you need a large computational domain if you want to model this part. So how do we approximate, how do we minimize this aspect? And the same way, we also need to capture the small eddies, small phenomena in order to study the physics behind it. So that means you need to have two scales of problem actually to begin with. So that means any numerical model which you try to develop should handle these two aspects. So that was the overall goal, mostly in the numerical model community. So if you look at the scales, as I told you, there are two different scales. If you look at this particular picture, wherein you can see that there are different phenomena, which is in the time scale. If you look at it, there is from 1 seconds to 100 years, as well as the spatial scale, basically the domain length or whatever, maybe you try to vary. It can be from millimeter to a kilometers. So that means different phenomena are going to exist. So for these different physical problems, people try to use different levels of modeling. Say if you look at it for a if you want to model a small time scale or small horizontal spatial scale, like for example, soil structure interaction or wave breaking or turbulence aspect, you need to concentrate on a highly resolved models. Okay, or you call it as a depth resolved models. That's what we normally use it. There you have a wave structure interaction process is going to be dominant. Where in the case of a large time scale, say for example, if you are going to have a 10 years duration, or after 1 year, what could happen to my entire shoreline? So it's basically a morphodynamics modeling, wherein you cannot use the complete physics, wherein you have to go for a empirical or statistical modeling based modeling. So that means when you go for an increasing level of approximation, you need to have a lot of approximation involved in resolving the spatio-temporal scale problem. The other aspect is, one more important aspect is how do we model the propagation bathymetry, the run-up shoreline inundation modeling. Those are going to be varies from hour to year. So there are different classifications in which we can able to categorize the model. And people have basically developed different types of modeling in these different regions, right? So try to cover up because you cannot adapt one particular model for all the scales. So that was the idea behind doing it. But later part of it, people also thought, okay, fine, we really don't need to. I mean, is there any feasibility wherein you can actually have only one model wherein you can able to cover all these entire scenario? So that is where the hybrid modeling comes into picture. This is just it's mostly the hybrid modeling in the today's context is more or less well understood when compared to 10 years back. But still there are a lot of challenges. Still there are a lot of things which we can able to improve on. That's what we will try to discuss in this particular talk. And as I told you, the challenge is basically in the ocean engineering community is basically a large area that is of hundreds of square kilometer, as well as the wave conditions are completely non-linear. It also coexists with the current as well as the sediment movement. And if you are interested in small motions or small eddies, the viscosity and turbulence are going to be important. And of course, these turbulence or viscosity will have some influence in your motion characteristics when you have going to have a violent wave impact onto the structure, or you are going to also need to model the air as well as the water, particularly, for example, in the case of renewable energy, for example, oscillating water column, you have to model both the aeration part as well as the fluid as well as the wave part. And then, of course, you are also trying to deal with the hydroelasticity. That means the structure is not going to be considered as a rigid anymore. It can be flexible. So how do we model the hydroelasticity problem? So these are the challenges which we have, particularly in terms of the domain size as well as the physics of the problem. But when you try to do it mathematically, when you try to see the fluid mechanics problem, there are basically two unknowns. One is the velocity and pressure in the basic fluid mechanics problem. However, in the case of ocean engineering, we are going to also have a third unknown, which is free surface. So that is also going to be a challenge. So how do we solve this problem? People have come up with different aspects to sort it out. And the numerical methods in ocean engineering, there are different types of numerical methods that have been adopted, like boundary element method, finite element method, finite difference, finite volume, or particle-based approach like SPH, MLPG, particle-based finite element. There are a lot of methods which are available. And normally people think that, okay, fine, one method is superior than other method. It's not like that. Each of these methods has their own advantage as well as the disadvantage. So the idea of the research community is try to identify the disadvantage and try to improvise it. So that is how these methods have been developed to the vast extent. So the important aspect is try to identify the disadvantage and try to overcome the disadvantage by using some numerical treatment or numerical aspects to it. So that means you cannot say that one method is superior. So that is not the correct word to use it. And the second aspect is, once you identify the problem, so the second important aspect is for which type of problem, which physical processes are going to be important. So this has to be identified before you try to understand the mathematical process and which physical process you want to resolve and which physical process you don't want to resolve. Because numerically, if I want to resolve all the physical process, it will be time consuming as well as it will be challenging aspect. So the idea is try to identify the problem which you are going to deal with, and then check whether the physical process which we want to do is important or not, and then try to come up with a mathematical model, and then your governing equation with the boundary condition, and then you try to solve it. So if you look at the physical process in the case of a large domain as well as a small spatial temporal domain scale, I have classified into different. Just a simple example. Actually, it's not a straight. It's not this is the only one, but you can also have multiple physical problem which you want to deal. So if you look at it in general, in the today's numerical modeling aspects, we can see that the nonlinearity in the fluid is going to be the is considered, is required, is the need. Okay, and if you look at the surface tension, most of the physical process, it is not even required. So that means it is not that much of dominant. That's what I would say. It's not. Wherein other aspect like viscosity and turbulence may or may not depends upon the problem which you want to identify. And introducing turbulence in the numerical model has to be very careful, because numerical model is also, some of the numerical models has their inbuilt dissipation characteristics. So that means introducing turbulence has to be proper, or it has to be used only when it is required. Don't need to adopt the turbulence modeling for all the class of problems. So that is one of the things which you have to take away, that we have to consider. So in the case of a wave structure interaction, there are two classes of problem. Once you normally go to the experiment, which is a traditional way, go to the experiments and then try to do the experiments and try to find out what is the physics behind it. And the second aspect is the numerical model, which we call as a numerical wave tank or experimental wave tank. It's basically a reproduction of the same thing what you are going to do in next. And in the case of a numerical modeling, there are different approximations. One, you can solve the full Navier-Stokes equation, or you can also do approximate, like assuming it's a potential flow, whether it's a fully nonlinear or a weakly nonlinear, or a depth averaged, that is the Busnik's model. And then you also have a different class of numerical methods. So the blue one is basically the methods which at IIT Madras, which we have developed over the past 20 years or so. And one of the important aspects in the numerical tool development is whichever numerical model, whichever numerical method you try to use it, the numerical method has to handle both the non-braking as well as the braking process. See, if you look at some of the existing, it may work very well for a non-braking, but it may not work for a braking process or vice versa. So it has to be simulate these two extreme lower as well as the higher end perfectly. And then, of course, it has to handle the multiple structure interaction as well as the splash up and all those things as you see in the reality. And for the industrial aspect, the simulation must be computationally efficient. So that is what we have to deal with this entire aspect of it. So the other aspect to the numerical model is the difference between the verification, validation, calibration. So there is a lot of confusion. I mean, for a young people, they have to understand the differences between this verification validation. If you look at the validation, it is basically whatever the model which you develop, try to validate with the existing literature or the experiments, how accurate or how good your model is. In the case of verification, it's nothing but you develop a numerical schemes and how these numerical schemes are working for different spatial as well as the temporal discretization. So that is basically the verification process. And the calibration is basically, suppose if you're trying to do some kind of a statistical modeling within the numerical model or empirical part, how do we adjust the coefficients in such a way that we can able to have a better results in for the validation. So that is the differences which one need to understand before you try to develop or try to use any numerical modeling aspects. And at IIT Madras, we try to develop the time domain models, particularly the starting from the Navier-Stokes model to the fully nonlinear potential flow theory to the Bushnig's model. But of course, the computational cost is going to depend upon physics of accuracy which you do. Suppose if you look at here, the computational cost is much higher for a Navier-Stokes model. Is of course the physics we are trying to resolve as good as possible. Wherein if you look at the Bushnig's model of potential flow theory, the computational time will reduce when compared to modeling the fully nonlinear when try to model the Navier-Stokes model, but the physics in accuracy has been reduced because we try to do some kind of assumption approximation in order to solve the particular problem. So that means, is there any feasibility? Is there any way wherein you can try to combine these models? That is basically the hybrid modeling, wherein you try to come up with a fluid. That is the far end, you try to use a potential flow theory, and near to the structure, you use the Navier-Stokes model and try to increase the physics in accuracy. In the same time, you reduce the computational cost. So that was the idea of this hybrid modeling. So that is what we are working in for the last 15 years or so in this particular domain. So that means before you go to the hybrid modeling, you should also know about, you should independently develop and try to find the expertise in this NS model as well as the potential flow or the Bushnig's model. So that was one of the intention before you go for adopting for a wide variety of problem. And in the case of a Navier-Stokes model, again, there are different classifications wherein you try to do whether you're modeling the partition approach. That means you have different codes and try to put together in one single tool, or you try to model the entire stuff in a simple implicit expression. That is basically the formulate as a simply implicit equation, both modeling both the rigid body or the flexible structure along with the fluid. So that was the idea in the NS type of modeling for the 3D. In the case of porous or vegetation, suppose if I want to model a vegetation, which is quite common in hydraulics as well as in the ocean engineering nowadays with the coastal engineering aspect. So the other in those cases, whether you want to model the microscopic level, whether you want to try to see the each and every configuration, each and every shape of the rubble mound stones. But of course, you can model it, but the computational time is going to be very, very expensive. But the other aspect is try to do a macroscopic approach. I just want to understand only the general behavior of the flow. I'm not interested in the minute details. So for example, I want to know how much the wave is going to damp, or what is the damping effect, what is the energy loss load. So if you are interested only in this aspect, try to choose the microscopic, not the microscopic approach. So that is how you have to incorporate these things in your Navier-Stokes modeling. So this picture most of you might have seen. So this basically gives how the waves are being generated and what is the wave periods that is ranging, whether it's from 0.1 seconds to 24 hours, what are the different types of restoring as well as the forcing part of it. And mostly in the ocean engineering, people will try to work on this two area. That is only the one is the ordinary gravity waves, as well as the second one is the long period waves where you have a storm surges, tsunamis. So for this particular region, people normally use the wave structure interaction process where you have most of the structures present. Mostly people will use potential based approach, and you can also use the RANS, LES, direct numerical simulation in this particular region. So in this particular region, one of the quite common one is the potential flow solver. Uh, this is well established in 1976 initially, and later from 1990s to 2005 or so, it is well developed, and people are very convinced with this particular method wherein you can able to have more than 95% of accuracy. So the concept is very simple. You use Eulerian step, and then you use the Lagrangian step to update to the next step. So I'm not going to the detail of it because of lack of time, but this is what the method is. But this method is now well established, and there is no need to do further research in this particular fluid. How do we solve the wave part of it? And over the, I mean, from 2004, we are developing this particular method on potential flow. We applied it to a wide variety of problems like tsunami run-up, or for a submerged bore, or for standing waves, or for a floating bodies. All those things have been well established, and it can actually have a 95% accuracy with respect to the experiments. So far we have done in this particular one. So the idea is, but the problem is, as it is a potential flow, it cannot able to handle the wave breaking, or it cannot able to handle the viscous effects when the viscous effects are going to be dominant. So those are the two limitations in this particular approach. The second set of thing is going to be the how do we model the storm surges or tsunamis, which is going to be a shallow water equation or the Busnik modeling, whether there is a weakly or fully nonlinear. There are different varieties which are available. Basically, how we basically approximate the horizontal velocities, whether it's in the case of a shallow water, it is a constant, where in the case of a Busnik's model, there is a varying level of approximation which people are normally employed. So in the past, these we also developed this finite element based Busnik's model, wherein we applied it to, mostly these models will be applied for modeling a large scale problem, like a triangulity under the inside the breakwater with the combined effect of reflection, refraction, as well as the diffraction process. But recent years, people are also adopted this particular model, particularly for inland waterways, which is quite popular nowadays in India, wherein you can able to see how the ship is generating the wakes and how these wakes are going to influence the bank, where the bank is going to get eroded, and how to protect the bank by using vegetation, whatsoever it is. So for these things, because it's a large domain, we cannot use a Navier-Stokes model to model this large domain. So in those cases, these Bosnik's models will become very handy. So these are the two classes which we have developed over the past years. And the other one, the case of a Navier-Stokes solver, is basically there are two different classifications. One, we try to use the Eulerian, or you use the Lagrangian, fully Lagrangian, and there are different aspects of domain, whether you discretize the entire domain or you embed the domain by using a multiple phases. That is, you have an air phase, water phase, as well as solid phase. So in IIT Madras, we also developed these both these class of modeling, both the domain discretized as well as the domain embedding approach. Also, it's been developed. And one of the domain discretized, particularly in the case of a mesh-free method, which we are working on, is basically the MLPG, is basically meshless local petrogalerkin, which basically comes from a hierarchy of finite element families. And in this one, basically we try to use the test and trial function. If you are familiar with finite element, we use a Galerkin approximation. Here we use a Petro-Galerkin, wherein the test and trial function will be in a different functional domain. And then instead of using the finite element as a global formulation, we will use a local weak form. And then we really don't need any mesh to it. And then we try to use only the particles to try to find what is happening to the nest here. So last 15 years, we tried to develop this particular method. And in 2021, we got an invitation to review this development, which we have done both combinedly with at IIT Madras as well as at the City University of London, UK, wherein we both City and IIT has a long-term collaboration, and then we try to develop this particular MLPG for application to ocean engineering. We apply to a wide variety of problem, both 2D as well as to the 3D. So this paper you can actually review, wherein we have tried to explain different aspects, different applications, varying from elastic structure interaction to a fixed body with the floating bodies, with the vegetation, with the porous modeling. So we have addressed a lot of aspect with the two-phase modeling, how MLPG can able to take into consideration, particularly the application to a sloshing. You name it, we basically did most of the application. But one of the issue with this particular MLPG is that it is still under research stage. We still have a lot of challenges. We still have a lot of issues. And one of the thing is we try to overcome these issues. So that is the idea behind the entire development of this particular aspect. And parallelly, we also develop another solver, which is based on traditional approach, based on finite volume method. This IIT Madras right now, it's an open source. We are actually already, it is there in my website. It's open source. You can download the entire tool. You can apply it to a wide variety of problem, wherein we applied it to, basically we apply to most of the problem, including the floating bodies. Right now, we are recently developing, as well as we have both non-conservative as well as a conservative form of RANS solver. And we do also have the turbulence modeling within this tool, and it's completely MPA. It's a parallel execution in the cluster. And one more thing is, one of the important aspect of this RANS 3D solver is it basically couples with the potential flow solver. So that is one of the introduction which we have done, wherein we try to couple this with potential flow solver, wherein you can actually reduce your computational time drastically. So that is what we have developed. I'm not going to the detail of these numerical methods, but it's already published. It's already there. Open source, you can actually download, and then you can basically use this. You can also use it not only for ocean engineering application, you can also use it for hydraulics applications. If you are interested in some of the dam break flows or hydraulic jumps, it's already been, we have already tested for some of the spillways. Of course, it can be used for those aspects too. And the most important thing is, if you use MLPG or if you use the RANS solver, the computational time. So how do we reduce the computational time? So the reason for reducing the computation, one is computational time, but that is not the only thing which we are looking for. If you use a Navier-Stokes solver, by default, no matter which type of method you are using, which type of approach you are using, there is going to be energy loss when you want to do the simulation for long time as well as for long duration, or for a long distance. Okay, so in order to overcome this energy loss in the Navier-Stokes solver, the idea is to try to couple it with the potential flow solver, which does not have this energy loss aspects. So that means one can use the different theories between the far field as well as the near field. So so for that, there are two different approaches. One we call as a domain decomposition. We also try to develop the one-way. That means only one-way communication will be there. And there is a two-way communication will also be there in the domain decomposition. And the second aspect is the functional decomposition, again with and without structure. So both these aspects we have developed at IIT Madras. So one-way communication is you try to take the FNPT and give these velocities, information, pressure, everything as an input to the Navier-Stokes solver. Therein you can able to reduce the entire computational time, as well as increase approximation, increase accuracy. So that's what we found out by using this coupling approach. This is one way. You can also use the Boosnix model. Like you have a long domain, you model by using Boosnix, and then near to the region alone, you use, suppose if I want to model a breakwater alone with the Navier-Stokes solver, you can use it. So that was the idea behind it. And then we also successfully did recently by coupling the Boosnix model with the particle-based method, wherein you can actually use an entire three-dimensional one and try to study the interaction with the viscous effect. So that was the idea behind this one. And in the case of a second approach is basically the hybrid. So in the previous one, there will be only one-way communication. That means the Boosnix model will try to give the information only to the Navier-Stokes solver, but the Navier-Stokes solver will never return back the information to the Boosnix model. That means it will not run, two things will not run parallelly. So the idea is, how do we do the two-way coupling or a strong coupling? So that means you don't need to do only in the space, but also in the time. So we right now it is almost 10 years. It's 2014. If you look at it, these concepts which we have developed, and it is very successful till date, wherein we also try to couple it in space, as well as we also try to have an algorithm to couple it in time. And then we try to see, okay, fine, when you are going to have a potential flow solver over here, and then you are going to have a Navier-Stokes solver, and the waves will go over here, it interacts with the structure, and then it will return back. The return back effect will also be felt by the potential flow solver. That means you will run the entire two solvers parallelly, and then it will also exchange the information in real time. So this is what we did in the previous years, and then we see that there is a drastic reduction in the computational time. So this computational time is 10 years before. So even 10 years before, when you want to run a simulation of 8 hours, we try to finish in less than 2 hours. But now if you look at it, this will be much faster because of the increase in computational power nowadays. The other aspect is basically the functional decomposition. So in the case of functional decomposition, the idea is very simple. Instead of doing the domain-wise separating the solver into potential flow solver or a Navier-Stokes solver, in the functional decomposition, what we normally do is you take a Navier-Stokes equation. We know the Euler equation. So if you subtract the Navier-Stokes equation, Euler equation, you basically get the complementary part. That is only the viscous part of it. You solve the viscous part alone using CFD and add it with your incident wave solution, you will get a total wave field. So the idea is you still use the Navier-Stokes. That means you still use the viscous effect. So that means your computational time will be drastically reduced instead of solving the full Navier-Stokes equation. So that was the idea in the case of a functional decomposition. So again, this functional decomposition is also quite successful, wherein you can able to, but again, there is some limitation related to the wave breaking. You cannot able to model the wave breaking part, as well as, so that is one of the challenge, but rest of things it's can able to still adopt this solver. And the last one, which before I finish, is basically the coupling. You don't need to couple. One way is, recently, if you look at the floating bodies with the renewable energies, there is a lot of interest in the mooring lines. So I need to also couple the floating body along with the mooring line with the complete fluid part. So we also try to develop the schemes, particularly to couple the floating bodies with the mooring line. Of course, this floating body, you can actually use it in a different scale, and the mooring lines you have to use in a different scale, and then you have to couple it, and then there is a orientation. But the concept is well established, but the challenge is computationally you have to try to evolve basically the how we basically interlink the two things. So that is one of the challenge, but concept wise it is well established nowadays. And one of my student, Dr. Siddiq, he also did this particular aspect by coupling with the far field is basically the potential flow, which is based on hydrospectral method, and near to the field is based on Navier-Stokes equation, and the mooring lines will also be adopted along with this entire process. And then he tested it for a mood decay test with the complete physics involved in it, and then compared with the experiments. Along with that, both with the regular waves as well as the random waves. Again, with the experiments, we got a very good comparison with the motion characteristics. apart from motion characteristics, the tension on the mooring line is also going to be critical. How the fair lead point is going to behave. So that also was quite decent in this hybrid modeling aspect. And one of the recent initiative is that as part of ISOP, this is one of the first comparative large scale comparative study. If I see wherein we release experimental data to the open public in 2019, to be frank. And then we invited different researchers within the ISOP community to come up and validate their own in-house numerical models. But we didn't specify which model to use. We didn't specify what type of modeling is required, but we just simply released two cases. One with the cylinder which is moving in a towing tank in a wave flume and then interact with the wave. The other one is having a fixed cylinder and then interact with the waves. That is a focused waves which we did. And then we invited people, and like we have seen that there are we got from 10 different countries having different types of numerical model which are either developed in-house or commercial softwares. We got for a fixed cylinder about 19 different solvers and 4 solvers for the moving cylinders. And then if you look at it, people have adopted different types of modeling techniques like a weakly coupled solver, a full Navier-Stokes solver, or a completely potential flow solver. They have not even touched the because it's not a breaking waves, it's only a deep focused waves. And if you look at the entire thing, what we have seen that most of the people right now adopting to the hybrid modeling concept, that is basically use at the far field, use a potential flow, and just near to the field, you use a Navier-Stokes solvers. And the second important aspect which we have seen is that irrespective of the method in which they have generated the waves, because in the lab we use the piston type wave maker to generate the waves, but in the results we have seen that people have used piston type, they have used different approach like glaciation type or Dichler type. All the types, irrespective of the types, we have seen that all of them got a decent results, and the results are between 5% variations are present. And we also measure the pressures. Pressures are also very well compared. So that means we can solidly say this nowadays numerical community is well developed in this particular area. And for the moving cylinder, we didn't get that much of people to participate because of the challenge it involves, because we have to move the cylinder for 15 meters and then it has to interact with the structure. So that means you need a really long computational domain. And so that is one of the challenge. So we did a decent analysis between these different solvers, and then you can see a complete comparative study between how people have developed, how people have obtained these results, and what is the conclusion, what is the guidelines which we can able to take out from this particular activity. So this is from 2020. We also recently did in 2022 also we have done one comparative study on the wave breaking on a vertical wall, which is a curved vertical wall in the large scale as well as small scale. And in the PAMCOMS, which is going to be held in IIT Madras in October, we are also doing another comparative study. We also released the data for the twin bots. So that is basically twin body application we are trying to do. So this is my last but one slide wherein what is the future? Still there is a challenge. But only thing which we can say is the concepts of coupling is well established right now. But still we can see that one is potential flow theory, another one is the Navier-Stokes solver. So mathematically at the interface is not satisfied. We are satisfying it only numerically. And then, as I told you, one is irrotational flow and another one is a rotational flow assumption. So again, that is a question mark, which you have to take care of it because it's only numerically we are solving, but theoretically and mathematically is still questionable. And the surface-based approach like Busnick's model as a challenge in the coupling at the interface, which we have to take care in the future. And then this overlapping zone, you have to predefine before you run the model. You cannot define at the later stage. So that is one of the aspects which we have to take care of it. And the last but not one is the future is how do you couple the numerical model with the experimental tag. So that is one of the aspects which we are trying to look at. So this is the recent facility which we have developed at IIT Madras to generate the waves for a very large, it's a shallow basin. So if anyone is interested, you can write a proposal and then you can come and access the facility. It's open to everyone. So the idea is how do we couple these numerical models and try to transfer to the experiments, or from the experimental result, how do we try to transfer it to the numerical? So that is the future. And the last word which I would like to say is the experiments and numerical modelings are not a replacement to each other, and both are important and both should go hand in hand. And this you should keep in mind. People in developing numerical model, they will say that numerical models are better, and people who are in experiment, they will say experiment models are better. But it's complement to each other, so that you have to take care into the future aspect to it. Okay, so with this, I would like to close my talk. I'm open for any discussion, and if you are interested in any of the tools, you can approach me. Finally, I would like to thank all the funding agencies who graciously supported our initiative, as well as the strength students who basically developed most of my codes. So I would like to thank them and dedicate this entire stuff to them. Thank you.
All right. Thank you, Professor Sriram. It was very interesting to see the different types of models that you developed. And I think this is going to be very useful for the PhD students. So nowadays we see a lot of students who can apply the models, but they don't know what is inside the models. So I think you gave a really good presentation so that the students can learn from it. And for researchers, it is exciting that you're developing these new techniques that can be applied for different applications. So thank you so much. Now, before we take questions related to the presentation, Vinay and I are going to ask you a couple of questions to get to know more about you. And
Yeah.
after this questionnaire, we'll open the floor for audience.
Right. Yeah, sure.
Right. So the first question we would like to know is, why do you study ocean engineering? Like, can you tell us what took you to ocean engineering and what is motivating you? And tell us your path, basically.
Yeah, my path, if you look at it, I am basically from civil engineering background. So when people study in civil engineering, they are either interested in fluid mechanics or in structures. So I am interested in structural engineering. But unfortunately, I didn't get through structural engineering, so I got opportunity in ocean engineering. So I stick to ocean engineering. Then I realized that if I might have studied structural engineering, I may not come up to this level what I have taken as ocean engineering. So that means in the beginning, after doing a BTech or B, everyone is interested towards their core area, correct? Structural engineering. So I am also like that, but I got an opportunity in ocean engineering, so I just went into it. Then I realized that, okay, here it has a very huge challenge when compared to the structural engineering aspect. So that's how I took up my entire career. And from there, I realized that, okay, fine, numerical modeling is one of my strength. And then I took up that part. So that is how it went into the entire. Yeah.
So you're a combination of ocean engineering and structural engineering.
Yes.
Now.
Yeah.
Sir, I just have one question, say if we as a faculty, sometimes, most of our time is usually engaged with research or administrative commitments or academics, right? So how do you balance your personal life as well as the, official commitments? Yeah.
It's a good question, but I am not good in managing both. Okay, professional life is different, and that is frank. So to be frank, it's work-life balance is difficult, particularly to begin with. But you have to cope up. I'm not good at it, so I cannot able to say that I balance like this. So that is my direct part.
True, because when I look at myself, I'm so disorganized. Sometimes I feel it, because of last minute commitments that we get it, or deadlines that we have it. Sometimes it becomes difficult to manage home as well as the office. So
yeah, it's the same. So I am also have the same aspect, but
it's a
somehow your other off
the-
has to your better off has to understand, and then you have to work. That's the only thing. Yeah.
Yeah.
Thank you,
I
sir.
think we just keep learning as we go.
Yeah.
Yeah. So we heard about your research so far. We want to know, what do you do outside of work? So can you tell us what are your interests outside of the work?
Outside of work, I spend some time with my kid, but she will always say that you are not spending time, but that is the one. And then I watch movies, TVs. So that's the most of the thing. I don't have any. I'm not good in sports. I'm not good in any of the other readings. Nothing. I'm not interested in any of this. So normally I watch movies, and then I spend time with my wife and kid going outside. That's it.
Yeah, I think most of us are movie buffs.
Yeah.
Sir, I have one technical question here. What do you think of improvements in the numerical modeling, especially in the last 10 years? I mean, how far we have reached?
Yeah. So if you look at the last 10 years or 15 years, previously people have used commercial software. Okay.
Yes.
And later people started developing the open source part, like OpenFOAM, and everything is picking up and picked up. And because of this commercial software, because the previously commercial software, if you look at it, they want it to be robust. So they don't want their code to break down. So basically you do some value, it will dump some value out. But because nowadays we have this open source tools, people try to, because running open source is different, running a commercial software is different. If you run a commercial software, whether you give some value, it will try to, because it's developed in such a way, where in the case of OpenFOAM, if you are not well, it will break down. We really don't know what the reason is, and student has to try to figure out what the reason is and why it is breaking down. So in that way, it is good that people try to learn what is there. Before 10 years, it is very difficult for them to learn what is there. But now, because of this open source thing, they try to understand why it is breaking. Once if the simulation breaks down, they will try to understand for what reason. They try to know what is current number. They try to understand what it is. But previously, they simply follow the steps and then they will do it. So that is the difference. And slowly, people try to get the interest, and who are good in developing, they try to develop the numerical model. So that's how that is a change which I feel when compared to previous years in the last 10 years in the mindset of the students particularly.
And just to follow up on Vinay's question, so what barriers do you think are still existing when we want to develop these numerical models further?
So I will not say any barriers, but rather I would say the interest from the interest and passion from the student side to try to venture into it, because there is no obstacles as of now. There are quieter literatures. There are a lot of varieties of methods which are available. So the only thing is students need to try to adopt which method is going to work best. So that is the only thing which you have to do. So I don't think there is a barrier. It's more about the interest and passion for the students to do about it.
Sir, in continuation to the same question, so I mean, what do you think in the next 10 to 15 years, what is the change that we can expect in the advancement of this numerical modeling? And what you would like to see?
So the advancement, basically what I would see is what I'm trying to feature is basically how do we adopt the AI and machine learning models, approaches, because AI and ML is basically a tool. Unless you really don't know what is the physics, you cannot able to model it. That is the physics informed. So basically the physics informed neural networks. That means right now we are discretizing the equations by using some of the methods, correct? So these governing equation has to be physics informed. We have to put in the physics informed neural network and try to. So that is one way to reduce your massive computational effort. And in the near future, what the thing right now people are working is basically within the suppose if you take a Navier-Stokes solver, within the Navier-Stokes solver, you have a turbulence modeling. So whether you can able to model only the turbulence part alone by using the AI, wherein because these are coefficient driven. So you have a machine learning and then try to driven these coefficient depends upon the physical problem. So that is one of the area which right now people are working on it, and there are quite a little bit of success in that particular area too. So that has to be taken forward into the next level. So that is what the future is to be in that area.
Thank you, sir.
And So my question is about, do you have a favorite paper that changed the direction of your research or that has greatly influenced your research?
I really don't pick any one paper because because during my PhD I read one or two papers that use for my potential flow theory from Wu and Etok Taylor and Prof. Chingwei Ma. That's all. But after that, I hardly, to be frank, I just go through, only sweep through the paper, and then I will not go into the detail of the paper. I will just sweep through and then see what method they have used. That's all. So not in depth. I have not gone. I don't have one favorite paper that can be taken off.
Sir, did you notice any difference in the publishing practices in your field, especially from the past to present?
Yeah, there is, of course, many people may or may not agree, but that is a fact. The thing is, if you are in abroad, getting through a paper in a very good journal paper in abroad with the foreign authors is easier. With the collaborators is much easier. And still that is one of the challenge, particularly from India. If you have only the Indian author's name, it is a challenge. Say, for example, I would tell my own example, even though even if you are going to publish it, it doesn't matter. This is what happened. So when I was in abroad, I put up some paper. It's one of the top journal, and it got published. And after coming over here, I published only with no collaborators, only with Indian Institute of Technology, IIT Madras. Then they told me, in one instant, they told me that this paper is not relevant to this particular journal. Then I shoot out an email that I already published this work in your journal itself. Then there was some consultation that has happened. So that is a top journal. That is one of the toppest journal in our field. The same thing has happened when I try to publish to another journal. Again, the same aspect. They told that this work is already developed at City University of London. The City University of London who developed that work is myself. So, so they even referred that paper, but they really don't. That is the scenario. So it's basically perception. So luckily now I overcome that particular perception. So now if I have my name into that, they never look at the country. They basically look at the name. So basically for a young researchers, that is one of the challenge that you have to come up. There will be initial hurdle. I had this hurdle in the first 1 year, 1.5 years. Then after that, I overcome it. So that is the thing. That is a reality. So I also hear this not only from our ocean engineering field. I also hear this from other department also. So this is the reality. That is the perception. So that perception one need to change.
Yeah, so I think we need to develop the collaborations in the initial stages. Maybe that.
No, not collaboration. That's what I mean to say. The collaboration, they are they are considering your work because of the collaboration, not because of the work that comes from India. Correct. So that aspect has to be. I mean, you have to change based on the quality of work which we do.
Mm-hmm. Yeah.
So collaboration is of course important. Collaboration is of course important. Collaboration will lead to a lot of other good things wherein you also try to expose, you also try to learn what is there in the practice. I'm not denying that, but you have to also present yourself without collaboration also. So there should be some work which has to be have individually on your own. So that has to be developed.
Yeah, sure. Thanks. And this is the last question from our side. So what are your suggestions for young researchers like myself and Vinay if we want to write a research grant? Like what are the tips and tricks that we need to know?
Yeah, for the research grant, it's a good question. If you, I'm not sure about other hydraulics, but if you look at ocean engineering aspect, it's a very narrow domain. And if you look at DST or SERB, they basically they have to fund in different areas, right? So ocean engineering is one of the area wherein there are very few applications itself. So if you have a very good quality proposal, so now come back to what is a good quality proposal. The good quality proposal is going to be basically when you try to look at any proposal, it should have a decent introduction or decent motivation, why we are going to do it, and what is the state of the art in that particular field, and what is the research gap. And that research gap has to be how we are going to address that particular research gap, whether that particular research gap is a viable, that the addressing how we are going to address is a viable option or not, whether it is practically feasible or not. That in order to show that it is practically feasible, you have to cite 1 or 2 papers or 1 or 2 works which you have done previously. And it should not be a mere extension to, it should be something unique. In that case, I don't think DST will reject. So this is the aspect which we have to, but the proposal, the presentation of the proposal should be very clear, and it should be visible. I mean, the presentation should be clear. So you should not have too many objectives. You should have too many scopes. You should have a simple scope, narrow scope, what you want to address and how you are going to address it. So so that is a thing which you have to look for when you. That is how I got most of the DST projects. And one go, I got about 7 DST projects. So this is what it is. So you have to look for that particular aspects in order to try to get it.
Okay. Yeah. Thank you, Professor Sriram. So now we'll ask the audience to raise any questions if they have. It could be about the presentation or in general about the career. I hope that should be fine. Yes, so we have a question from Binit. Binit, please unmute. Yeah.
Yes. Good evening, sir. Very informative and interesting slides I have seen. As one question is there. Suppose we want to develop like both numerical and experimental work. Again, this is just a basic question that I would like to understand whether there is a dominance of this experimental studies over numerical studies, or numerical studies are dominating over the experimental studies, or they are both interdependent.
So I would say they both are interdependent. Okay, so see, for example, it is going to depend upon this, whether you are purely going to concentrate on the experimental work, or whether you want to develop the numerical model. Say if you want to develop a numerical model, you definitely need experiments in order to validate it. Correct? In order to validate, and then you can able to do a lot of parametric study in the numerical model. Wherein if you use experiments, you may not be able to run a lot of experimental data, because you have a lot of parameters and it is laborious, and you have to spend a lot of time. Correct? So both should be complement to each other. But by doing, I mean, if you want to become a very good numerical modeler, you should definitely do experiments. Then you know what are the things you can able to reproduce in the numerical. What are the things you cannot able to reproduce in the numerical? Say, for example, if you really do a flume tank, and if you have a current which is going to generate, in the numerical model, we normally use a uniform current. But unless and until when you go and do the experiment, then only you know that the current generation in the experiment is challenging. Right? So that student has to understand. You cannot simply say and then they will not understand. You have to go in person and do the experiments in order to understand what is the difficulty in the experiments in order to put the numerical part. And when there is a difficulty in the experiments, then okay, fine. For these reasons, I want to do the numerical part, and then I want to develop the numerical part. So both has to be complement to each other. One is not a replacement. That's what I finished my slide that's saying that people think that, okay, numerical is dominant and experiment is important. These are two different category of people who are developed over the traditionally, right? So yes, that has to be changed, right?
Sir, I totally agree with you. One more question is there. Suppose some experimental work, it is very difficult to establish. So whether we should go for the numerical modeling, or we should again rely on, or we should wait for that experimental studies.
So it is, for example, if you are trying to understand one particular physics of the problem, And for that particular physics of the problem, if the numerical models are going to be challenging, correct? And the same thing, external models can also become challenging for that particular physical problem. I would rely mostly on the experimental work because the numerical models have a lot of approximations. We really don't know whether we are trying to reproduce that particular physical problem. So you have to go with the physical problem and then try to look for the experiments or the numerical part.
Thank you, sir. Thank you, sir, for your suggestion.
Thanks.
Yeah, that's from my side.
Yeah.
Dr. Anand.
Yeah.
Thank you.
Yeah. So we'll take 1 or 2 more questions from the audience because we are almost out of time. So please
Sorry,
unmute yourself. All right. So yeah, I assume there are no more questions.
Yeah, sure.
So, yeah.
Fine. Thank you.
Yeah.
Thank you.
Prof.
Thank you for the nice initiative. Thank you for the nice initiative. I think you should carry on with this initiative and then try to get a lot of people into it.
Yeah.
Sure.
Yeah. Thank you so much for joining us.
Thanks.
Yeah,
Thanks.
Thank you. Thank you all. Bye.
Thank you.